All right, so now that we've got our equations for acceleration, velocity, and position as a function of time for an object in simple harmonic motion, let's write the definition of simple harmonic motion. So these all are as a function of time. Let's write the acceleration as a function of displacement. Right, we've got an equation for velocity as a function of displacement, and then acceleration as a function of displacement is typically written like this: omega squared x. Right, so this would be the maximum acceleration would exist at the maximum displacement. However, if you just write it as acceleration, you have an equation as a function of acceleration as a function of displacement with a certain angular frequency. Okay, and this is actually the definition of simple harmonic motion. Okay, so if there's a question that is ever asking you, right, is this object in simple harmonic motion, there are two things that you need to be looking for. Okay, is the acceleration proportional to the displacement? Okay, and then the second thing is there a restoring force that always opposes the displacement, right? Right, those are the two things that you're always looking for an object to be in simple harmonic motion. So a restoring force opposing the displacement means that there's a negative in that equation. Okay, so I want to talk about, with this equation here, A equals negative omega squared x. For different objects, different oscillating objects, omega squared can be found in different ways. Right, in your textbook, I'm going to refer you to some pages in your textbook, and they will do something that's kind of confusing. Right, they will say, for simple harmonic motion, A is proportional to negative x. All right, cool. And then they will say A is equal to, right, turning a proportionality into an equality, equal negative kx. And you might think to yourself, where the heck does k come from? Is that the spring constant? What is that? This k is a k in like your math class, a random constant. Okay, so it doesn't represent anything physical. Okay, it's just k for constant. But we know that this constant, the thing in front of x in this equation, actually should be omega squared, right? I don't know why your textbook does this. Like, why confuse people? The constant in front of x in the definition of simple harmonic motion equation is omega squared. Okay, the constant is omega squared in front of x. And it's especially confusing because we, some stuff that oscillates in simple harmonic motion might be a spring. The abbreviation for a spring constant? K. So when I was first reading through the textbook, I was like, okay, that's not the constant in front of omega squared. The spring constant is a different relationship. So just warning. Okay, so just like I was saying, A is equal to negative omega squared x, where A is acceleration and x is the displacement from equilibrium. So that's an equation form. And oftentimes you are given a graph when we're looking at simple harmonic motion with acceleration in meters per second squared, and displacement on the x-axis in meters. And what would that equation, or what would that graph look like? Well, we've got a proportional, the relationship between acceleration and displacement is proportional, where this would be the slope, right? So it would be proportional with a negative slope. Some stuff to notice is that this line has limits, right? Something like a pendulum that we've had oscillating doesn't oscillate with infinite amounts of displacement, right? And so at the end of this line, from this, you can read the maximum displacement. On the other side, on the negative end of the x-axis, you'd get the negative maximum displacement. And this line should be symmetrical. The slope, right, if you find the value of the slope of this line, it should be equal to omega squared, right? The value, the absolute value should be omega squared. Okay. And then remember, again, that omega is the angular frequency, so it's 2 pi over the period, or 2 pi times the frequency, and the units are radians per second. Okay, so oftentimes you can find that slope and a question will ask you to find the period of oscillation of the simple harmonic oscillator. Okay, so here's an interesting question. Is a oscillating spring in simple harmonic motion? Well, we'll find out. Let's remind ourselves about what a spring does. Remember last year we did an experiment where we stretched a spring and we measured the force with different amounts of stretch of the spring, which we'll label as X. And we found a linear relationship where the slope was the spring constant in newtons per meter. It told us how stretchy the spring was. Okay. All right, so the question is if a spring is in simple harmonic motion, right, the acceleration is a negative proportional relationship to the displacement, and the restoring force is always opposing that displacement, either slowing the displacement down or actively pulling an object towards the equilibrium point. So let's say that we have a string or a spring that's attached to a block. Oops. That spring, no matter what, will always be pulling the block back towards an equilibrium point. So the equation for a spring, from this equation, the spring force is equal to negative K times the displacement, where in this case, K, right, this is why I pointed out that other K. K is the spring constant. Right. We also know that the spring constant is the net force, right? If we're assuming there's a frictionless surface that this block is sitting on, we know that we're experiencing a net force that's equal to MA. And that net force is the spring force. So we can say the spring force is negative Kx, and that's equal to MA. And so we can solve this for acceleration. Acceleration equals negative K over M times X. Right. So I'm going to box this, but this equation is not in your data booklet, I don't believe. Let's check really quick. Nope, not in your data booklet. So this is something you would be expected to derive yourself. So from this, we have an equation for a spring, the acceleration versus displacement for the spring. We still haven't answered, is this oscillation in simple harmonic motion? Well, we've got acceleration equal to negative some constant times x, right? Where that constant is K over M. Right? If we compare this to the definition of simple harmonic motion, acceleration is equal to negative some constant times x, where that constant is omega squared. That tells us that, yes, right, the spring is in simple harmonic motion. Right, the acceleration has a negative proportional relationship with the displacement, and the acceleration is always opposing the displacement, as indicated by these negatives here. Right, and we can also see that for a spring, omega squared is equal to the spring constant over the mass. Right, so it's really important that you can take a force, any force, and set it equal to MA in order to solve for A and come up with an equation for simple harmonic motion for any oscillating object. And then once you've set that equation equal to acceleration and see that it's proportional to displacement, the constant in front of x will be equal to omega squared, and you can use that to solve for things. All right, what other things could oscillate in simple harmonic motion? I don't know, anything that's bouncy, stretchy. You could look at the Foucault pendulum at the convention center. You could bounce on a yoga ball or something as a chair. How could you test it? You could put a motion detector over the top of your head as you're bouncing on the yoga ball and see if you get a nice sinusoid. That would be a way to go. All right, here's a check-in. I'm going to run out of time on this video, but take a screenshot and see what you can answer for this question.